Hi everyone, my name is Roberto. I'm so happy to be here today at Redundancy 2021 and have the opportunity to share a little bit of my work with Rafael, Salim, and Daniel. This work is about field trace polynomial codes for secure distributed matrix multiplication. I'm going to start introducing a scheme for secure distributed matrix multiplication introduced by Shang and Tandon. Their version for the SDMM problem starts with a user that has two matrices, A and B, and the user wants to perform the matrix multiplication AB with the help of N servers. The user also wants the information theoretic privacy guaranteed even if these servers try to collude in order to learn some information about matrices A, B, or AB. The main goal of this scheme is to speed up the computational time to get the product AB. There are some works in the literature covering the secure distributed matrix multiplication problem and some of its variations using really nice techniques to approach these problems, such as studying the degree table of polynomials, entangled polynomial codes, and root of units. Most of the techniques to approach the communication costs for the SDMM problem mainly focused on reducing the number of servers to minimize the communication costs. The main idea behind that is the more servers used to compute the matrix multiplication, the higher will be the communication cost. We'll be showing here today that this is not the case in general. There are some tools that can be adapted from repairing Reed-Salomon codes to the SDMM problem, which will require more servers, but the total communication costs will be reduced. Let's start with this example of a traditional polynomial scheme using 3 servers. A user has 2 matrices, A and B, that for now we assuming the entries of these matrices are at the field F16. The user will be generating 2 random matrices, R, same size as A, and S, same size as B. After that, the user will be forming 2 polynomials, F and G, and then the user will be selecting 3 evaluation points, beta 1, beta 2, and beta 3. In the next step, the user evaluates F and G at beta 1, and send evaluations to server 1. Then evaluate that functions at beta 2 and send it to server 2, similarly to server 3. Let the polynomial age be the result of the product FG, which has degree 2. In this scheme, the user will be interested in finding the polynomial age evaluated at 0. Each server then can compute the product, and then they will be able to send it back the result to the user, and the user can interpolate the polynomial age and decode the function, the product actually, AB, which is actually the evaluation of the polynomial age at 0. Let's understand a little bit about the communication rate. For that, we need to explore first the communication costs. Remember that in the first phase of the communication part, the user sends evaluations of polynomials F and G to the servers. Evaluations of F will be matrices of same size of matrix A, and evaluations of polynomial G will be same size as matrix B. So that the upload costs will be 3 times AB plus 3 times BC, where those are symbols in F16. For the download phase, you're going to download the evaluations of the polynomial age, which has same size as matrix A times B, the product AB, which is denoted here by matrix C. The download cost will be 3 times AC in terms of symbols of F16, the extended field. So since the part of interest has size AC, our total communication rate will be AC over 3 times AB plus 3 times AC plus 3 times BC. So our main contribution in this work is to improve this communication rate by contacting more servers. Before I show you the case where increasing the number of servers increase the communication rate to use for the user to perform the product A/B, I will present first the problem for repairing Reed-Salomon codes for distributed storage by exploring a naive approach to do so. In a distributed storage system, a user has a file F, which is a vector of key entries over a field E, which will be distributed among n servers. A technique to code this file is encoding through a polynomial of degree k minus 1. Therefore, each evaluation F is stored in n servers. The goal of this scheme will be to retrieve any node erased. So if the node 5 fails, contacting k nodes provides key evaluations of the polynomial of a polynomial of degree k minus 1, allowing polynomial interpolation and therefore the retrieval of the node 5. There's a new technique used to repair Reed-Salomon codes introduced by Mary Wouters and also explored by Alexander Barg, which achieves the optimal repair bandwidth for one erasure. The setting will be same as before, and evaluations of polynomial F will be distributed among n servers. The only difference is that we are going to see each evaluation as an element of an extended field E of the field F. This extension allows a new approach using the field trace function, which will use more servers and download less information from each in a way that the total download cost will be smaller than the naive solution presented in the last slide. The reason for that is if a field E is an extension of degree F of degree S, then each symbol in the extended field E corresponds to S symbols in the smaller field F. So transmitting field trace of the evaluation instead of the evaluations by itself allows to retrieve the node 5, contacting the nodes and downloading only this expression of symbols in terms of the smaller field F, which is the optimal bound. The feasibility is ensured by constructions given by Alexander Barg and Mary Wouters. Last year, Olga Milenkovic published a paper with an elegant solution to repair simultaneously 2 or 3 failures. I'd like to highlight here, as the number of nodes contacted increases, the retrieve evaluation, to retrieve the evaluation of interest, the download cost decrease, which goes asymptotically to S symbols of the F, the smaller field, which correspond to 1 symbol in the extended field. Motivated by these repairing techniques for Reed-Salomon codes, realize some similarity with the secure distributed matrix multiplication problem using polynomial codes. We asked ourselves, is it possible to use the field trace function similarly, that is, contacting more servers and reducing the total communication costs? The answer is yes, but there are 2 main differences. The first one is we know beforehand which evaluation we want to retrieve. And the second one, the upload costs must also be considered in this equation. So let's explore this example with 4 servers. Similarly to the last example with 3 servers, the user has 2 matrices, A and B, and wants to compute the multiplication AB, now using the help of 4 servers instead of 3. In the first step, the user generates a random matrix R, same size as matrix A, and then we'll generate the matrix a matrix S, same size as matrix B, and build the polynomial F and the polynomial G. Then they also the user also selects some evaluation points to encode matrices A and B and send each evaluation to each server, similar to the last case. Now, with the shift in the polynomials f and g by alpha, where alpha is a primitive element in the extended field f16, the user is interested in repaired evaluation of the polynomial h at alpha. The servers are now able to compute the product, and instead of sending back the evaluations like the product by itself, they're going to send the field trace of the result. So using the result of each server, the user is able to compute the product AB by computing this equation over here. So the equality follows from the definition of the field trace function, its property regarding the F4 linearity, combined with the fact that the evaluations are actually in the smaller field F4. There are like some other properties regarding the field extension, such as the primitive polynomial x to the 4 plus x plus 1 equals to 0. Let's try to understand a little bit about the communication rate for this case. We have sent 4 evaluations for each polynomial f and g to 4 servers. Since the size of matrix A is A by B, the upload cost regarding the matrix A is 4AB. For matrix B, the upload will be 4BC. So the total upload cost will be 4AB plus 4BC in symbols of the extended field F16. The change will be for the download costs. In this case, each server sends field trace of the evaluations of the polynomial h, downloading 4 times AC. Note that the download is in symbols of F4, the smaller field, whichever symbol can be identified as half of each symbol of the extended field F16. The total communication rate will be given by this formula over here. Note that the upload is more expensive, while the download is less expensive. Since the upload depends on B, we can find some parameters for the size of the matrices where the FTP code outperforms the previous schemes. The condition is given by this expression in the bottom. Although this example explains the repair technique for the SDMM problem, it's not an efficient way to perform the matrix multiplication. The reason I'm saying that is each server has to compute the matrix multiplication for matrices of the same size as the original ones. To realistically speed up the computational time, it is necessary to consider a more general version of this problem, which starts with 2 matrices, A and B, divided in L smaller ones, denoted by AI and BI, in a way that the product is the sum of the product AI, BI. Therefore, each server will perform the multiplication of 2 matrices in smaller dimensions. For this general formulation, Rafael and Salim proved that there will be always parameters L and T to speed up the computational time. So in general, FTP codes will require a small additional operation, which is entry by entry and has a low complexity. Therefore, for large enough matrices, the extra computation is asymptotically not significant when compared to the whole matrix multiplication. With the general scheme introduced and considering the partitioning and security parameters L and T and some prime numbers in the ascending order, we can consider prime powers of Q0, prime powers Q0, and then another prime power Q, which will be like Q0 to the power of the product of all those prime numbers. Consider now the matrices AB in this extended field with Q elements. There is also this server parameter, which is essentially the number of servers needed to retrieve the partial multiplication AI/BI. To perform this scheme, we will need NL servers. Given all of those parameters, we can show that there exists an FTP code which computes the matrix multiplication with the total communication rate given by this expression over here. Note that the first part of this expression depends on B and is related to the upload costs, while the second part does not depend on that. So the question right now is, are there parameters L and T, or size of matrices, that makes this total communication rate better than the non-traditional codes? What is shown here is that for every traditional polynomial code scheme with partitioning parameter L and security parameter T, there will be a constant key which depends on L and T, and there will be also an FTP code with the communication rate higher than the one for any traditional polynomial scheme, whenever the dimension of the matrices respects this inequation over here. The main idea to prove this is by constructing an FTP code and compare it to the trivial bound given by n greater than L for traditional polynomial schemes. So far, what you know about this new approach is that the FTP code's construction has some suboptimal steps, which depends on the repetition for this scheme to retrieve every part for the matrix multiplication AI/BI. The good news is we already have some preliminary constructions which outperform the FTP codes and do not utilize the field trace function. However, they haven't been generalized yet. So there are a lot of places to get some improvement for the SDMM problem. And what we have shown here today is that the general SDMM problem has not been really well understood yet. Thank you so much.